Hello, my name is Suzanne Schwest, and my partner Aditya Mohan and I will be going over ranking-based optimal resource allocation in peer-to-peer networks. To cover some background, peer-to-peer networks are networks in which two or more users share data and access information without the need for a separate server. Some examples you may have heard of are Skype, LimeWire, and BitTorrent. There are many different resource allocation methods, and some are far better than others. Some examples are statically based allocation, priority queuing, and bandwidth throttling. Priority queuing is based on real-time network conditions, and bandwidth throttling has to do with limiting bandwidth for excessive consumers. However, all of these have a common issue. They're susceptible to free riders or even suspicious attackers. Now, the paper that we focused on covers selfish peers and resource allocation. Peer-to-peer networks have been seeing recurring periods of growth over the years. However, they still struggle with free riders due to their nature. The paper that we read has a proposed mechanism of checking the history of each peer based off publicly available information to protect the user's privacy. This mechanism, which, as I said, uses a ranking system influenced by behavioral histories, works as described here. Peers can improve their rankings by contributing resources to the system, as there's a direct link between contribution and ranking. The mechanism promotes sustainability and cooperation for the network, because without an incentive, it is not likely that users will consume and contribute equally. Lastly, it's important to note that it also limits strategic behavior, such as users setting themselves up for their own benefit, disregarding everybody else. The reference paper also offers sound solutions for limiting the risk of free riders and attackers. Low behavioral rankings make suspicious nodes easily identifiable, and admission control can then block those nodes that have bad rankings, which improves quality for admitted competing peers overall.
So parameterization and our methodology. So we are basically using two parameters, namely utility function parameter and the social welfare function parameter. And that controls the sensitivity of the changes, which we will observe later on. And then we have an important concept known as threshold rank. So how does that affect? As long as the ranking is not greater than the threshold rank for a peer, a competing peer is allocated resources that satisfy the minimum resource requirement of the competing peer. If the source peer is congested, then the ranking ratios are used rather than the rankings, and that is because ranking ratios actually cause the allocation change in that case. If we observe the equation over here, we can observe the amount of allocation that is being given to a peer is affected by its rank, its ratio with the other competing peers, and the threshold rank of the system. Moving on, we are having utility and max-min fairness functions, which are also used in our model. So the utility function is designed to capture the source peer's preferences for allocating resources to different peers, taking into account factors such as historical behavior, resource contributions, and service consumption. Second to this, the concept of max-min fairness is central to the resource allocation mechanism discussed in this paper, and this means that the resource allocation strategy seeks to ensure that even in a competitive environment, no peer is unfairly disadvantaged or no node receives more bandwidth than requested. Looking at the graph on the right side, we can notice that if the social welfare function alpha is less, then we can observe more drastic changes into the allocated resources for a specific peer, and if it's higher, then it hardly affects, which is in direct correlation for the maximum fairness. Then another important aspect of our model is admission control, which primarily speaks about admitting new nodes and throttling it, and of course its objective is to ensure fair and efficient resource allocation even when the source peer is congested. So one of the challenges that this paper addresses is when the source peer is congested, allocation of resources must meet capacity constraints while maintaining fairness. So this is achieved by implementing resource constraints and with a specific focus on the capacity constraint for a specific resource. Looking at the right side, we can notice that for a friend, it allocates more resource, but for a stranger, it allocates less. And as and when the history develops and the capacity increases, we can notice the stranger being allocated more resources.
This model described in the previous slides is better for the user as it improves quality of service and therefore user experience. Additionally, it's better in the long term for the network's sustainability, as its inherent linear scalability allows more users to join without straining the network too much. Security-wise, the admission control handles the blocking of malicious peers, further incentivizing use of the system. Lastly, the parameterization allows the system to adapt easily to real-time network changes, which is extremely necessary given the volatility of networks. Now, what makes this solution different? The first thing is improved security. As a service session always involves at least two peers, their behavioral histories can be verified by both peers involved in the session. This allows confirmation of behavioral data without requiring a user to reveal private information. Secondly, we have the application of the maximum fairness that was discussed earlier. This allows for the best possible minimum required allocation for each user, which betters the user experience overall, no matter who you are or what your behavioral ranking is. Now for some successes. We think that this paper has a great foundation with solid principles, which allows for sustainability of the platform. The approach is innovative and has the unique structure of the optimized allocation function that we talked about before. Lastly, it lays a very solid groundwork for future development of user-centric peer-to-peer networks. Now for some critiques. One challenge that the paper openly acknowledges is the limitation of considering only stationary peers. We would like to explore in the future this functionality along with the dynamics of competing peers, accounting for changes in peer behavior over time. Secondly, the paper primarily focuses on optimal resource allocation without really delving deeply into the dynamics of resource scheduling. The dynamic aspects of resource scheduling should be investigated further, considering factors like varying workloads, network congestion, and other evolving things like user preferences. This could improve the adaptability of the model to changing network conditions. Lastly, the model relies on predefined parameters and utility functions. While the utility function and method for admission work very well in their environment, as we discussed, we think the integration of machine learning techniques could enhance the model's adaptability by allowing it to learn more and evolve based on observed network behavior.
So we have a case study here which is on BitTorrent, and we think that it reflects the methodology discussed in this paper by a very large degree. So these are listed features of BitTorrent's application, and some of the key takeaways of these features which reflect our model are the tit-for-tat mechanism and the choking and optimistic unchoking. And they basically reward the peers who are actively sharing with the network. That happens for the tit-for-tat mechanism, and it throttles simultaneous connections with other peers, and unchokes appear to discover potentially faster connections in the choking and optimistic unchoking technique. Some other work which is being done by peers on similar grounds is a game theory which is being incorporated into P2P systems, and it focuses on factors such as cooperation, competition amongst peers, and incentive mechanisms. And we have blockchain and decentralized applications, which brings in a more secure form of networks and a more robust form of memory allocation techniques. And of course, we have the distributed systems and its applications in P2P networks. Now we have a proposed solution here which expands on the research and our own components included, and we're basically proposing a streaming service which is made using BitTorrent, which includes WebRTC technology which is used for streaming, and since it's open source and community driven, it's good for the society, and since it's open source, it also is cross-platform compatible. And if you're coupling BitTorrent DHT, which is decentralized hash table, then we will be able to achieve trackerless operations, and bootstrap nodes will be, if they are implemented, then that will be also great for admission mechanism and so on.
Throughout this project, we were able to gain a deeper understanding of the intricacies of peer-to-peer networks and their applications. Additionally, we were able to learn about industry standard security measures and best practices. Lastly, we gained a strong foundation in the field of resource allocation optimization, which will provide us with a wealth of applicable knowledge moving forward in our field. We proposed the potential for an optimized streaming platform, as mentioned before, and we could see ourselves working on this as a possibility for a focused project in our academic future. Thank you so much.
Thank you.